Welcome to the Battery Testing Mentor podcast about battery testing, battery validation, battery safety, and also battery regulations. My name is Johannes, and we are exploring here every 2 weeks this very amazing topic. If you have any questions, any feedback, or just a small hint, do you want to get in contact with the guests of our show today, then just reach out to me by the typical channels of LinkedIn, YouTube, email, and so on. And I bring you in contact or consider your feedback. So as I said, today we have some guests here. I'm very honored to have here with me two founders, basically, of a small or startup of a new company. On the one hand, Paul Büschel, and on the other hand, Thomas Günther. Welcome to the Battery Testing Mentor podcast.
Yeah, hello, Johannes. Thank you.
Hello. Thank you for having us.
Yeah. So maybe before we start talking about your company, can you give like a short introduction about yourself, where you're coming from, what you're doing in the battery space? And then, we can dive into your company.
Yeah, so I'm Paul. I'm a mechatronic by trade, but realized during my studies that I'm more into the electrical engineering field. And in the end of my studies, I started working with batteries. So starting with my diploma thesis, I began working with impedance spectroscopy on lithium-ion batteries, and then continued my journey at the University of Technology in Chemnitz on the chair for measurement and sensor technology. Continued there with impedance spectroscopy for the diagnostics of batteries, and moved on to algorithm development, mainly for the diagnostics of batteries with time domain data. So going a little bit off-road from the impedance spectroscopy path towards direct analysis of time domain data. In 2016, I've joined ThyssenKrupp with the goal of implementing advanced measurement technology into formation equipment for the battery manufacturing. And this was the first time where I got in touch with very large scale manufacturing. So before that, I was aware of the manufacturing process of lithium-ion batteries, but there I realized what it means to have it at a large scale. So I became responsible for the hardware development in the formation team over at Thyssen. So we did formation chambers and all the electronics required for it. And in 2022, I have left Thyssen, but I've gained a lot of insights into problems with large-scale manufacturing. And I realized that a real pain point of battery manufacturers is the aging step in the formation, as it breaks the whole process time-wise. And I started working on the specific measurement issues that come with the aging. And this later became Limatica in 2024.
Mm-hmm. Thank you for this summary. Thomas, do you want to say some sentences about you?
Yeah, cool, for sure. Thomas Günther, my name. My background is information and communication technology. So let's say always on the interface between hardware and software. I did work at Chair for Measurement and Sensor Technology here in Chemnitz for 6 years, always with a focus on reducing complexity of battery diagnostic approaches in terms of computational complexity and hardware complexity. And later on, I've had the opportunity to move to the team of Paul at Thyssen roughly 1 year after Paul has already started there. And together with Paul, we focused on formation equipment. I, entered the team as a measurement engineer at the beginning, and soon became responsible for, hardware-related software. And let's say, had the my mission was to, let's say, get everything running, get the infrastructure up and running, and let's say to tackle the problems when bringing some, let's say, measurement technology from a prototype to a product, which for the gigascale factories, it's quite challenging task. And this was my focus there. And later on, as Paul already said, left this together and started Limatica with a different mission. Yeah.
Yeah. Yeah, as you said, you have your own company now. It's called Limatica, and you are focusing basically on this part of end-of-line testing when it goes into the formation, right?
This is I just jump in. It's almost correct.
Okay,
We are focusing on the aging step in the battery production, which is almost end of line. It's a step that is used to detect defective cells after the formation step, and it's extremely time consuming with very little information outcome. And this is essentially the focus we have in manufacturing.
Mm-hmm. So basically, to elaborate a little bit, how is this done today? So basically, the cell is produced, it goes into the formation, and then you sit down basically and watch the cell age in some way, and then decide if it aged well and the cell is okay, or if something happened and you need to get rid of the cell. Is this the right description?
From my point of view, yes. So it's, let's say, lots of effort in point of time and very little insight in terms of information, process feedback, and so on. So after initial charging of the battery during formation, you need to know, did it actually work out? And the current state of the art is, let's say, putting cells into a shelf, check the voltage, wait for a prolonged period of time, and later on check the voltage again. And this is more or less a guess on, do I actually have a good or bad cell? It's one indication. It's not the only one currently used, but currently it's one of the main bottlenecks in terms of process time in the cell production process.
Yeah, because it just takes a long time, right?
Yeah, days to weeks, depending on the current on the manufacturing process and depending on the cell type, and for sure depending on, let's say, the particular manufacturer. So the process steps are always kind of, let's say, secret sauce. So it varies depending on who is actually producing the cell, but in general we are talking about days to weeks.
Mm-hmm.
I just want to add that the moment the cell goes into aging, it had quite a journey behind it. So it started when you fill the cell with electrolyte. Then the cell becomes electrochemically active. So electrochemical processes are starting inside the cell. And this is where the problems start. You need, after the filling of the electrolyte, the cell needs to soak. That means that the electrolyte can fully penetrate the electrode material. In the same time, because the cell has an initial voltage of around 0 volt, corrosion processes occur at the anode side current collector. So you have a kind of a conflict. You want to shorten this process step of soaking, but you want to also have the electrodes fully wetted. So this is the first problem. No measurements available for that, essentially. So what is tried is ultrasound measurements, but they can hardly detect microscopic defects due to physical constraints of the method. So then the cell goes into something called the pre-charge step, where the cell voltage is initially lifted above roughly 1.5 volts, depending on the chemistry, to prevent the corrosion and to be able to have more time for the wetting process of the electrodes. So then the soaking continues, and after a prolonged period of time, roughly 1 to 2 days, the cell goes into formation. During the formation, the cell is fully charged and cycled. Of course, if you have a really defective cell, you will realize it during formation, but what you will not realize are, let's call them soft faults, like soft shorts or plating related effects and the like. So to identify cells that have these kind of soft faults, the aging step is performed. It's essentially less aging in the meaning of the word, but rather a method to identify weak cells. So what is done is cells are measured at the beginning of the aging. So the open circuit voltage of the cell is measured at the beginning of the aging. Then the cell is stored for a prolonged period of time, like 5 to 10 days. And in between and in the end, the voltage is again measured. And from the voltage drop, one estimates if this is a good or bad cell. So a cell with a high voltage drop is a bad cell. A cell with a low voltage drop is a good cell. And then after cells have passed this first grading step, let's call it, there might be an additional charge-discharge step to get to the final SOC and the real end-of-line testing, which usually incorporates pulse testing and AC impedance testing at 1 kilohertz and the like.
Yeah. Okay. So basically, we see there is kind of a lot of challenge, kind of a lot of improvement potential. I mean, I guess a lot of the manufacturers would love to kind of cut out this whole time completely. But this is not the approach you are going in to improve the situation, right? Like you are not getting rid of the aging, but kind of getting rid of the bad aging, to put it simply.
And the final goal would be to remove this long aging period, because it's only there to identify bad cells via voltage drop. And to have some significance in the voltage drop determination, so in the voltage drop that is measured, one needs this long period of time. And with our method, we are aiming on getting the information on the cell, if it's a good or bad cell, earlier in the process. So, and finally, our dream would be to remove this aging period, because it's an expensive step.
Mm-hmm. Yeah. So basically, you started your company a year ago, roughly now. I mean, last year. You started with this goal of, as you said, removing this whole time spent. Where are you on your journey now? Like, how far ahead are you already?
So with the method, we are able to discriminate good and bad cells quite fast. So we have tested cells from manufacturers that were quite fresh, where the time needed to discriminate the cells was roughly half an hour. So we would have been able to tell within half an hour if it's a good or bad cell, compared to days. The goal would be to improve this further, to be able to discriminate more grades. And this is what we are working on right now. We are starting measurement campaigns with different cell manufacturers on this specific goal. So measuring more and more cells to get more data to improve the method, to be able to discriminate cells further, not just good or bad, but also some graduations in between.
Mm-hmm. Okay. Do you like how do you validate that you really have a bad cell? Do you afterwards like cut it open and have a look basically, or do you then just put it in the aging and say, okay, there was really this voltage drop?
The latter. So together with the manufacturers, we are running in parallel to their process, because cell manufacturers do not really want to change the process until the new method is fully proven. So what we do is we run our measurements in parallel, because we have a passive measurement method it does not influence the cell. So the cell manufacturers are usually fine with that. So we run our measurements, they run their normal process, and we share the data of the aging. And then we use this to evaluate our method.
Mm-hmm. So basically, I mean, I know there is a lot of secrecy necessary, of course, to protect your method. But like, how or what are you doing? Can you describe this in a like short form?
Yes, I will try. So what we do is we analyze the voltage noise of the cell. So the voltage noise contains the information on the, let's call it, intrinsic activity of the cell. So if there's damaging processes ongoing inside the cell, the intrinsic activity is higher compared to a cell that is stable and settled, for instance. And what we do is we measure the voltage noise with high amplitude and temporal resolution. Then we do a data evaluation on medium-sized chunks of our data. So we do a windowed data evaluation on that. And then we analyze the temporal structure of the noise. And this is what's giving us the insights on the ongoing processes inside the cell. So on the intensity of the damaging processes.
Okay. And basically this gives you then in summary an kind of pass or fail value in the end,
Yeah,
right?
kind of. So you can think of it like a stethoscope. Yeah, it's a purely passive measure method. We connect the cells, the intrinsic activity, let's say the noise related to the intrinsic activity depends on ongoing effects inside. And like with a stethoscope, you will have different patterns in your signal. And based on these, we can discriminate the cells. And for now, we use these as a, let's say, grading tool to discriminate good and bad based on a voltage drop. So with the target to make it feasible as a, let's say, kind of drop-in replacement for cell aging. Because in cell aging, only the voltage drop is evaluated as a feature. And from our point of view, there's more. And the voltage drop itself is just the beginning to let's say, to get started as a first step.
That was the first part of our interview with Limatica. In 2 weeks, we will continue and then dive into some more technical aspects. How does this really work, what they want to achieve? It is super interesting. I can just recommend you to tune in again here at the Battery Testing Mentor podcast.